In this class, we're going to take a look at how you sketch the graph of a straight line. So notice I said sketch rather than plot. So we're not trying to plot a bunch of points and then draw a line through them, although we can take that technique to some extent. We are just trying to draw a sketch. And a sketch means that it's got a certain level of accuracy, but it's not a perfect representation, a perfect diagram of the line. If you're sketching curves, then there's probably a little bit more leeway for not having it quite as accurate because it's more difficult to sketch a curve. With a straight line being a fairly simple function, it should be reasonably accurate. And one of the reasons for that is a straight line is defined really just by 2 points. If you've got 2 points on a line, then you just need to draw the line through them to make the sketch. So that's one way that you can fairly accurately draw a sketch of a straight line. But we're going to consider a couple of ways to approach this. One is that more formal way where we find a couple of points on the line and we draw a line through them. But sometimes we just want to sketch, not as part of answering a question, but just maybe as a self-check mechanism. If you're working a question in straight lines and you're working it algebraically, as you probably would be, at that point you might not have a visual on the line, but having that visual, having that sketch to refer to can stop you making a silly mistake. It can help figure out some geometrical property that you can't see unless you can actually look at the graph. So we're going to consider how you can just very quickly sketch a graph in addition to drawing a more accurate representation. So we'll start with this line here, which is in the correct format, y equals mx plus c. And just think about how we could go about sketching that. Well, so for this one, let's start by taking the approach where we make 2 points on the line, and then we draw a sketch which goes through those 2 points, or a line that goes through those 2 points. So if you don't have any points on the line, you can just make them up. To make them up, just choose 2 different x coordinates. So let's say that we want x to be, well, keep it really simple. So you only need 2 points. So let's say x is 1 and x is 5, something like that. And to find the y coordinates that go with these points, you just substitute the x into the equation. That's how the equation works. So the y value that goes with that point would be 2 times 1, so 2 times x, 2 times 1 is 2, minus 4 is negative 2. So the y value there would be negative 2. So that gives us a point on the line, 1 minus 2. Similarly for x equals 5, 2 times 5 is 10, minus 4 is 6, so we get y equals 6, and we get the point 5, 6. Okay, so very simple, just choosing any x coordinate, because if you think about it, a straight line goes on forever, so every x coordinate along the x-axis is going to be on that line up and down the way somewhere. So these would be the x's, and we found the up and down values of y values. So we can just now take those 2 points. You would need to come up with some kind of scale for your x-y axis to draw it to a high level of accuracy. I'm just going to let sort of 1 centimeter or so be 1. So this would be like 1, 2, 3. So 1 along, 2 down would be like roughly there somewhere. So that's my first point. 5 along, so 1, 2, 3, 4, 5. And then 6 up, so 1, 2, 3, 4, 5, 6. Just counting it like that should give you an accurate enough representation. And then if we just draw a line going through those 2 points, okay, that's a bit of a curvy line, but imagining that's actually a straight line, then that is basically our line. But we can check that, because if we go back to the equation, does that fit in with the equation? Well, the line is sloping up to the right and fairly steeply, so it's got a positive gradient because it's going that way, not that way. The gradient is 2. This is the gradient. So does that fit in? Well, it does, because it's positive 2, and it's a little steeper than 45 degrees, and 45 degrees is a gradient of 1. So that fits in perfectly. Also, this point here, which was this guy, has got a y value of negative 2. The y value for the intercept is negative 4. So does that look like it could be minus 4 if that's minus 2? It does. It's perfect. So that's how we could fairly quickly draw a sketch there by plotting the 2 points. But sometimes we don't even need to be that accurate. So we could also just have sketched that one by saying, right, the gradient is 2, the y-intercept is minus 4, so you could just mark on minus 4, and then roughly draw a gradient of 2. We'll chat more about how to draw those kind of rough estimated gradients when we look at these examples here. In fact, let's do that now with this one, and then we'll come back to the middle one. So this is in the correct format. So we could actually go straight to drawing a pretty quick sketch here just by saying, well, the y-intercept is -1, the gradient is 3, so if -1 is where it cuts over the y, let's pretend that that's going to be like somewhere there, and we want to capture the gradient of 3. Well, like I kind of mentioned a moment ago, an m value of 1, so a gradient of 1, that's equivalent to a 45-degree line. So that's a really useful thing to know. So if you know that you've got a gradient of 1, that's going to be exactly a 45-degree line. But it's not such that a gradient of 2 then goes to 90 degrees. It doesn't quite work like that. If a gradient of 1 is 45, gradient of 2 is just a little steeper than that, and gradient of 3, 4, so they just incrementally increase in steepness. So by the time you get to a gradient of 3, you've not gone up to like 90 degrees, some like vertical line, you've just gone a little steeper than 45, so it's maybe something like that. So that gives you a really quick way of sketching that line. We could then take the same approach that we did over here to actually plot the points, but if you are just working a question to do with this line algebraically, and you just want a quick visual, that's a great way to do it. I mean, that would only take 10 seconds to draw. I mean, literally just x, y-axis, mark on the y-intercept, estimate the gradient, and you know what your line looks like. That's particularly useful if there's multiple lines. If you had a second line and you did the same thing and plotted it like that, if, for example, you were trying to find where those lines intersected, or if you were working some geometry problem around those two lines, having that quick visual is really powerful. Even though it's very basic, it's really powerful to validate that the work you're doing, the solution you're presenting makes sense. Without that, without being able to see that, you don't have it in your head, so it's very difficult to imagine what it looks like. Okay, this one is a little different because the format is not correct. It's not y equals mx plus c. We're trying to figure out how to sketch this guy. We've got a couple of options. We can either just do what we did here and make up points regardless of the fact that it's in the wrong format, because when we sub these numbers here into the equation, it didn't really matter that the equation was in the correct format. It doesn't matter here either, but we might need to work a little harder to get the value. So let's actually start by doing that, and we can just choose similar points. So letting x equal 1, that's always going to be a good call. If we do that, we would get 3 times 1, so 3 minus 2y equals 5. So we'll need to work this one a bit more. So minus 2y equals 5 minus 3, which is 2. So y equals minus 1. So x is 1, y is minus 1, so we get the point 1 minus 1. Choose another value for x. Let's go for maybe 2 this time. So 3 times 2 is 6, minus 2y equals 5. So again, just moving that 6 over, we get minus 1, and then we get y equals minus 1 divided by minus 2. The minuses would cancel, and you just get 1 over 2. The only slight issue with that is that these points, so that point there would be 2 and 1/2. These 2 points are fairly close together. Are they enough to give us a good sense? They are, but I would maybe advise trying to separate your points out a little. So this would work, but let's just park that and choose another value. So let's choose x equals, let's just go for 5 again, like we did up here. So if x equals 5, 3 times 5 is 15. Minus 2y equals 5, rearranging the equation again to get minus 2y equals 5 minus 15, which is negative 10. Dividing both sides by minus 2, and you would get y equals 5. So that tells you that the point 5, 5 also lies on the graph. So because these are separated out a little more than these two, it's going to be slightly easier to draw that sketch. So what I'm going to do, I'm just going to erase this here, and I'm going to fit the sketch in between. So we're just going to go ahead and plot on those 2 points. So just checking the numbers to make sure you get a suitable scale. So we're only going as high as 5 in both coordinates. So let's take this one first of all. So one along and one down. So let's say that's one along and one down. It's like there somewhere. And then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's going to be somewhere there. So we get those 2 points and just running the line through them. Then that should be what the line looks like. We can check how accurate that is because if we know the gradient and the y-intercept, we can check that they make sense with the line that I've just drawn. So to do that, we need to rearrange this original formula. So if we rearrange that, we would get minus 2y equals negative 3x plus 5. And then dividing both sides by negative 2, we would get y equals negative 3 divided by negative 2 is just 3 over 2x. And then it's going to be 5 divided by negative 2, which is minus 5 over 2. So does that fit in? So 3 over 2 is 1.5, positive 1.5. So a gradient sloping up to the right, 1.5 is a little more than 45 degrees. So that looks perfect. That fits in really well. It's almost 45 degrees. Y-intercept of minus 5 over 2, that's minus 2.5. Well, this point here was at minus 1, like down the way, the y coordinate. So if that point there is minus 5 over 2, in other words, minus 2.5, does that fit in? It does, yeah, because if that's minus 1, then minus 2 would be like there, minus 2.5. And that's the way it should be. There shouldn't be any inconsistency between your algebra and the graph. It doesn't matter how you approach this question, whether it's a rough estimate, like just making a quick sketch, or if you're plotting points or rearranging the formula, they should all tie in together. It's the fact that we can take these different methods and make them try to tie in together that kind of highlights any mistakes in our working. So that's effectively how you go about sketching graphs. So there's a more formalized version where you plot 2 points and you draw a line through. As long as you get your XY scale correct, that should be pretty accurate. And the second method is where you basically estimate the gradient, get the line in the right format, mark on the y-intercept, and just draw the line through that y-intercept using the gradient. That relies upon the fact that you know that a gradient of 1 is 45 degrees, and any variation on that just kind of floats around 45. So anything less than 45 or less than 1 would be a little shallower, anything steeper would be slightly more than 45, and a gradient slightly higher than 1. So I hope that makes sense, and I hope that this is useful to you if you're studying straight lines.